Now, can you hear me? Okay, excellent. Thank you very much. Good morning, everyone, and welcome to the 3-minute PhD contest. This is a competition that challenges PhD students to present their very complex topics in just 3 minutes and making it very clear and engaging for a broad audience. So this is a true test for communication skills, and it's an essential part also of learning how to disseminate science and promoting also open science in future. So I think this is an excellent exercise for our students, and I think this is also a great opportunity for all of us to see what our excellent PhD students are doing all across the 9 universities of UNITE. So indeed, today we are thrilled to have here 9 candidates, 2 candidates from each of the 9 UNITE universities, representing a wide range of disciplines. And as I said, the presentations will showcase the excellent research that we are doing at our institutions. We have a jury of 9 panel members composed of the different profiles we have at UNITE. So we have academic professors, administrative staff, and students from bachelor, master, and PhD. So thank you very much also for your contribution. We are excited to share this exciting event on YouTube, on the UNITE channel of YouTube. And to make it more accessible, it will have automatic subtitles so everyone can follow. So please excuse if there are some mistakes of the automatic transcribing. So as I was saying, beyond the contest itself, which is also very important, this is an incredible opportunity for us to witness groundbreaking research, connect across our institutions, and of course, celebrate communicating science efficiently. So without getting any longer, I would like to welcome our first participant. Well, this is me. I'm Cristina Canal, the first participant. These are all the attendees. You can come in, Honorata. Our first participant is Honorata Pochurach from Wrocław University of Science and Technology, and the title of her talk, or her thesis, is How to Reduce the Risk of Automated Guided Vehicles. You will see that there will be a clock appearing on top of the slide. Yeah, you can press here, and you have the pointer. Okay. So, thank you.
Okay, so why do people tend to like automation? The answer seems to be easy. In automation, these are technologies which can perform tasks with no or only minimal human intervention. That's why now we can see automation solutions everywhere. Look around. Automation is omnipresent in our houses, in our cities, in our work. And, oh, yeah. Yes. And we know that everything started in internal transport. Automated guided vehicle is a cart which follows a defined path, runs, and navigates by itself. Automated guided vehicles, known as AGVs, are popular in factories and warehouses and are used to transport parts and products. AGVs are cheaper, faster, and smoother than people. But there is a little problem. Companies have money and resources to implement a system of AGVs, but they are not aware of every risk. Collisions, power failures, mechanical problems are common risks for every AGV system. People don't like to talk about their problems, and the same goes for companies. Every risk generates new cost and affects the operation of a company. For continuous development, companies need to change their approach and try to cooperate and learn from each other. My risk management method will create a bridge between workers at all levels of company, AGV manufacturers, and regulatory authorities. It will foster collaboration and safe and efficient operations. This collaboration and smooth flow of information will affect not only companies, AGV producers, or regulatory authorities, but everyone in this room. The quality and price of final product will depend on how this product will be transported. This final product, sooner or later, will reach us, end users. And in the era where automation transforms our life and industries, the safety and reliability of automated guided vehicles are no longer optional. They are essential. My research delivers a framework which ensures that AGVs will operate with the highest standard of safety and trust. By focusing on both innovation and safety, we can ensure that AGVs become reliable partners in our industries. I invite you to consider how these insights can shape the way we approach automation. Thank you very much.
Thank you very much, Honorata. And now we are moving on to the next candidate, Mario Kircher from TU Graz, and with the title, Manufacturing of Polymer Electrolyte Fuel Cells, Novel Characterization Method Accelerates Electrode Development. So please, Mario.
Thank you.
It's here on top.
This is
Yeah.
Okay. Alrighty, let's start off with a quick question. So who here wants to save polar bears from extinction? In any case, yes or no, lean back and enjoy the next 2.5 minutes. My name is Mario Kircher, and I'm doing my PhD at the Institute of Chemical Engineering and Environmental Technology at TU Graz. I work on the development of electrodes for polymer electrolyte fuel cells within a Unite-based cooperation with FAU Erlangen in Germany. My research colleague there is Adrian Baumunk, and he does his PhD at the Institute of Power-to-X Technologies on the use and application of gas diffusion electrode half cells for electrode characterization. Our common goal here within this project is to unite the half cell and the fuel cell to have a novel, more powerful tool for electrode characterization for fuel cells. To understand our approach, let's start with how these two setups are actually working. So in a fuel cell, here on the right, hydrogen is fed as fuel to the anode, where it is oxidized into protons and electrons. Protons travel through the polymer electrolyte membrane, and electrons take an external pathway as electric current to the cathode. There, they recombine with oxygen to form water. A GDE half cell here on the left is a more basic research tool where only one reaction process, and usually that's the cathode, is investigated. So the cathode is very similar to the fuel cell. However, protons are directly delivered by a liquid electrolyte, and water is released into this electrolyte. So while the half cell is a simple, fast, and actually powerful tool for fast electrode screening, it is not as realistic in terms of operating conditions as the real fuel cell. So our goal was to, so the fuel cell, on the other hand, is a usually too complex whole system for pure electrode development. So our idea was to combine the half cell and the fuel cell to create the GD plus PEM, or three-quarter cell, as we would like to name it, here in the middle. Essentially, it's a half cell with the membrane integrated between the electrolyte and the cathode, and that changes everything which is going on in there. So it's still a very simple and more powerful hands-on tool like the half cell, but protons now have to travel through the membrane, like in a real fuel cell, and water has to diffuse out of the cathode, like in a real fuel cell. So the cathode is not exactly like in the real fuel cell. And there is no time here to show you numbers and figures, and I don't want to bore you with that actually, but what I can tell you from the results we have obtained so far is that this system appears to work very closely like a real fuel cell, and that heavily aids us now not only in electrode development, but now additionally in membrane development. So that, so is our dream, could help to spread and commercialize the fuel cell by the end of the day as a sustainable energy converter, and then that would be our contribution to save polar bears. Thank you. Sorry. I opened it. Sorry.
Thank you very much, Mario. I'm amazed because they are not only keeping on time, but they have extra time left. So this is very, very challenging, I would say. So now we have a candidate from the House. So let me introduce you to Patricia López from Universitat Politécnica de Catalunya, and the title of her talk is From Lab to Life, How Hydrogels Are Changing Medicine. So please, Patricia. 1 y 2. Y el puntero, no sé dónde está. Al revés.
Once upon a time, the idea of flying was impossible. Talking to someone on the other side of the world, impossible. Growing new tissue inside of the human body, impossible, until now. In 3 minutes, someone somewhere in the world will suffer an injury which their body can fully heal. In those 3 minutes, well, 2.5, I'm going to tell you how we are working to change that. You have to trust me. Our body has an incredible and amazing ability to heal, but sometimes need help. When tissues are severely damaged by an injury, a disease, or whatever, the healing process became slow, inefficient, and sometimes incomplete. But what if we can give our bodies new amazing tools in order to heal faster, better, and stronger? And that's where my research comes in. Hold my pipette, I got this. Indeed, I work with hydrogels. Let me introduce them. They are soft, squishy biomaterial, you have to think in a jelly, which mimics the extracellular matrix. It's the natural environment which supports our cells. Have you ever heard of collagen, alginate, or even hyaluronic acid? Probably yes, from cosmetic. But guess what? What they can do for your skin, they can also do for your body. They have an amazing ability to regenerate tissue. But how it works? Inside your body, they work like an architect, guiding your cells to the right places in order to improve the healing process. And I am working to make them even better. How? Modify them with peptides. Peptides are tiny molecules that can give hydrogels new amazing skills. And we have a lot of options. You can select whatever you need. For example, you can select peptides that works as defenders, killing bacteria, or as a boosters, guiding cells to the right places to grow, proliferate, and so on. So they are totally amazing. You can select whatever you need in order to improve your implant, or even combine to get many activities in one hydrogel, all in one. And guys, it's exactly what I'm trying to do. I'm trying to generate a new antibacterial hydrogel to the ability to improve the cell adhesion and also tissue integration. Why? Because in science, we are not just repairing what is broken. We are trying to redefine what is possible. Remember, once upon a time, it was impossible until now. Thank you so much for your attention.
Gracias. Thank you very much, Patricia. And now I think we keep in the health research. We have here Nuno Oliveira from Universidade de Lisboa with a talk on a vaccine against the African swine fever virus. So please tell us about that. Sí, arriba y abajo.
African swine fever. Rings any bell? If not, I can explain. It's a disease caused by a virus that infects domestic pigs, wild boars, and luckiest does not infect humans because it's very contagious, deadly in less than a week, no treatment available. For the past decade, it has spread through Asia, killing millions of pigs, and now it threatens to do the same in Europe and America. So we need a vaccine as soon as possible. But how the heck do we make one? And that's where I come in. Hi, I'm Nuno Jordão, and I come from Lisbon with a plan. Genetic modification of the virus. The idea is to create a live attenuated form that can still infect cells but at a much slower pace, giving the infected animal plenty of time to activate immune response, defeat the virus, and store some defenses for the future, just like a vaccine. But where to make that modification? The African swine fever virus is a capsule that stores inside a long line of DNA where it's written more than 100 genes. And each gene is like an instruction manual to build a protein with a specific form and function. We decided to focus on the viral gene I215L because it's the manual for a protein that it's very useful for the virus to infect blood cells and sabotage its antiviral defenses. So if we put defects on this gene, the resulting protein will be defective and the virus will be debilitated. Fingers crossed. But this gene has hundreds of letters. Which ones do we change? To know this, I used bacteria that are just like tiny protein factories. I gave them the DNA sequence of the viral gene with some changes that I wanted to try, and they gave me back mutant protein that I want to test. I saw which mutant protein presented the best defect, and then I knew the best change to make on the virus DNA. But I took a step further and I thought about a second mutation. Instead of changing the gene, I could also take it away, see what happens. So off I went to make mutant virus. I changed or removed the I215L gene on the virus DNA, and I also added a gene that produces a fluorescent protein. Why? Well, I cannot see virus on the microscope, but I can see cells infected by the virus. So catching the mutant virus was then a matter of searching and picking out the fluorescent cells. This way, I was able to get 2 tubes with 2 mutant forms of the virus. One where I changed the gene to produce bad protein, another where I removed the gene to produce no protein. And could they be a vaccine? Still work in progress, but I already saw that both mutants still can infect cells, and they seem to be much weaker than the original virus, especially the one where I deleted the gene, so I am pretty optimistic. And if anybody here also prefers to have a world with happy and healthy pigs, and also, let's be frank, with yummy bacon and jamon in our tummy, then cross your fingers with me for this to be a salvation for the swine. Thank you.
Thank you. Thank you very much. I mean, I don't want to stop eating Iberian ham. So now let's move on to the speaker coming from Politecnico de Torino. It's Paolo Han Beoleto, and the title of his talk is Elastic Smart Meta Devices. So please.
Hi, I'm Paolo, and even though you don't need a computer to listen, I'll switch to the slides. In today's digital world, sensors constantly sense and process data, leading to huge demand in terms of energy and computational power, fueling the Internet of Things, and especially machine learning. Traditional systems struggle to keep up with the requirements as they separate sensing, processing, and memory, dealing with a lot of battery consumption and especially slow data transfer. In sensor computing, rethinks this model by embedding computational tasks directly within the material itself, making devices faster, smarter, and more efficient. My research focuses on smart, elastic meta devices, dealing with mechanical metamaterials in order to process wave-based information directly with the material itself. The keywords are 3. So first of all, by inspiration. Thanks to the billions of years of optimization through evolution, we can take inspiration from structures recurring in nature. 2, mechanical metamaterials, as in nature. We can use microstructures to modify the macroscopic properties of the materials. And 3, immaterial computing, computing directly in the material, using its physical properties as computational units. Think through physics, as nature does, but you actually already do. For example, the cochlea. The cochlea senses a wide range of sounds thanks to its tonotopy, separating frequency content depending on the location inside of its spiral. Inspired by this, we designed a metamaterial resonator that is mimicking this frequency separation of the cochlea. Thanks to optimization, we were able to do immaterial computing inside of it, as we were able to map time domain signals into frequency-mapped outputs that were used to obtain, for example, a 98% in terms of spoken word recognition. This is a great result. And this tells you that if you put together bioinspiration, mechanical metamaterials, and immaterial computing, then you don't need a computer to listen. Think through nature. Think through physics.
Thank you. Right on time. Thank you very much. So we now move on to our candidate from TU Darmstadt. We have Jan-Peter Ceglarek here with the talk, Dear AI, Build Me a Satellite. Yes, yeah.
Hola, Unite. Hola, Jan-Peter. Yeah, I love satellites, and I think you should too. Especially I love building satellites, and this is why I do my PhD in this world. And I know that we all are asking ourselves the same question every day. How do I build the best satellite? I know it's a very common and usual desire. But we have now web shops out there, like Amazon, like eBay, where you can buy satellite components. And you can combine these satellite components, for example, for a CubeSat, as you see on the right side. You can combine these components in a million different ways. But how do you find the right combination of components for your use case? Because you have combinatorial space of amazingly large sizes, but you only need 10. So the question is, imagine a big box of Lego bricks. You grab in once, and you pull out your perfect 10 components for your use case. So you want to go to Mars, you want to go to Jupiter, you want to take infrared pictures, you want to send them home. These are different use cases than if you have them around Earth or around the moon or whatever. But you have to find the right components for the right use case. And this is the question I would like to answer with my research. How do you find the right components? And of course, as we do it now, we do it with AI, of course. Precisely is the idea that we have, you come in with a system idea, then you have this the combination of the human expert team, it's a human design team, and the AI, and you make design iterations. So you say, okay, build me this satellite, and then the AI says, okay, I propose you this 10 components. And say, yeah, but I like to do it a little bit this and that. And then you change and change and change. And this is an iteration together with the humans, because I don't want to replace humans, but to adjust to humans. And then this, on top, you can see these components database, which basically is a database of all available components. An outcome, something that we use in MBSE, so digital tools, so that the design that we design with my research, or with the tool that I propose in my research, that this design can be then used in further steps after that. This is the research. How can you use AI? Which AI is useful? Where is the end? What tools do you need to understand if the AI is useful? So many things. This research is not using large language models as ChatGPT and do things. We use old school machine learning, which was old school like 10 days ago. The research is fully open source. You can go to ai4ce.space to see the code and everything else. The website is nearly up. And yeah, I have 10 seconds to spare. Wonderful. Thank you.
Thank you very much. Thank you very much. I'm learning a lot today. Now we move on to our candidate from KTH Royal Institute of Technology, Amna Irshad, with the talk Massive Spatial Multiplexing in MIMO Systems. So please.
Thank you. And
yes, this one, yeah.
Hi. Let's imagine like we are in a crowded room as of today, and everyone starts to speak together, so it becomes harder for us to hear. That's what is exactly happening in wireless systems nowadays. With billions of mobile devices relying on 4G and 5G, the demand to have a higher data rate is skyrocketing. So let's look at the picture. we have different environments in which wireless signals is traveling. In some environments, like the signal is bouncing around many buildings or obstacles, while in the other, like it's having a less number of objects. Well, there is a case where there can be a clear line of sight path between the transmitter and the receiver. So no matter where we are, on city streets, inside buildings, or in open spaces, our mobile phones are always communicating with the nearby base stations. By 2030, it is estimated that around 6.3 billion 5G subscriptions will reach worldwide. So how do we solve this? That's where my research comes in, as shown in A. It plays a part with the antennas in our mobile phones that communicates with the base station. More antennas add to the network capacity, but how do we place those antennas? That's what my research is about. So I see that whether by moving the antennas or the optimal spacings between them, we can have a lot of difference between the data rates which we get. So slight changes can also lead to more capacity. But normally our mobile phones, they aren't stationary. We move them, we put them in our pockets, or we have them at different angles. So like for that, to cope with it, I have like this C, where I am considering movable antennas instead of the fixed ones. I had a comparative analysis of the movable antenna base stations with the traditional fixed antenna arrays, which can be like uniform sparsed, or it can be a wavelength sparsed as well. And I saw the data rates increase. So in the world where seamless connectivity is essential, so no matter, my research focuses on making the designs which are more flexible and adaptable. So no matter where we are or how we hold our phones, we always stay connected with higher data rates and optimized antenna locations. Thank you.
Thank you very much. And now we are moving on to our 8th candidate, coming from Aalto University, Kimya Tajik, with a talk on the fabrication of 3D directional fungal materials. So, please, Kimya.
Which one is yours?
Yeah, on top. Yeah, this one.
This one goes to next. Yes, thank you for the introduction. Yes, so my research is on fungal materials, and fungi has been used a lot in industrial biotechnology due to many advantages it offers. Fungi have metabolic versatility. This means that they can produce a wide range of materials, from antibiotics to polysaccharides. Also, they have high production and secretion ability, meaning that they can produce materials in high scales. For example, a strain called Trichoderma raceae can produce proteins in the scale of grams per liter, which is very high. Also, some strains of fungi are generally regarded as safe by FDA. Think of fungi that is used in food technology or in brewing. They have been used for a very long time. And also, fungi can produce materials like composites that are natural, sustainable, and also they reduce waste because they are both biodegradable and they can also be used to replace fossil fuel-based materials. And yet they require low resource to be produced. If you're interested in hiking and have been in the forest a lot, you might have encountered the mushroom in this photo. And if you were curious enough to take a piece as souvenir, you figure out that this is actually not very easy to cut through. It's so much stiffer than you would expect from an organic, fleshy material. So this exceptional mechanical performance is thanks to their oriented structures that you can see here in the figure. And they have these microstructures that are very hierarchical and organized. And this phenomenon has inspired scientists to produce lightweight materials with enhanced mechanical performance. And yeah, that is what my thesis is about. So during my thesis, I am going to first focus on employing and optimizing fabrication techniques such as 3D printing, and then find a way to incorporate stimulants that will induce directional growth in fungi so we get a better performance. Thank you.
Thank you very much. So we had already one candidate from each university, and now we move on to Guillem Lopez from UPC. That will tell us about the case for data center hyperloops.
Thank you for the introduction. I will start today with a very simple question. Have you ever listened that we are in the information or data era? Information or data has become the most important commodity in our society. But at the same time, we are generating an amazing amount of data every day. For example, Google tells us that YouTube generates almost 1 petabyte of new videos every day. And you may ask me, but Guillem, what is a petabyte? It is this amazing number that I have put here, which is 1 followed by 15 zeros. I still don't know what is that. So it's the equivalent of having 8,000 iPhones in storage. And of course, this is a problem. There are also other applications that are using this level of data. For example, machine learning, as some of my colleagues have explained, genomics, or physics. Of course, when we are in the petabyte scale, we need big supercomputers or data centers. This one is Mare Nostrum, which is very close from here. Maybe you have seen it, maybe not. So the question that I ask today is, how do we move a petabyte in this super machine? The best solution so far is using light through fiber optic. But if we want to use, for example, machine learning and train a new model, this will take us almost 1 week and megajoules of energy to move only this petabyte scale data. So I ask a question. Can we do better? Can we go faster than light? I will give you a couple of seconds. Maybe we need more than seconds. Of course not. I am not going to break any laws of physics today. I'm sorry to disappoint you. And I will be very happy to explain you our innovative solution. There is a key insight here, which is based on the fact that SSDs, the density has increased from 3 gigabytes per gram up to 1.4 terabytes per gram. And we are proposing what we call data center hyperloop. As crazy as it sounds, it makes sense. We are proposing to use small magnetic levitated trains in vacuum to move data from point A to point B, obtaining 600x in time and 400 in energy, solving one of the most common problems of computer architects, data movement.
Thank you very much. It's clear that our research is coming with very innovative solutions. And now we move on to our second candidate from Universidade of Lisboa, Nuno Miguel Cabecinhas, with the title, The True Power of Rainbows. So thank you.
I love rainbows, and so do the astronomers, because rainbows can help us answer one of the oldest questions of mankind. Is there life beyond Earth? With rainbows, made with light coming from distant stars, the astronomers can understand if there's a planet orbiting those stars. And they can even tell what their atmosphere is made of. And that is the key. Because if we find a planet like ours, orbiting a star just like our sun, and with an atmosphere similar to ours, then we have a strong candidate of a planet that can host life. And that, my friends, that is the true power of rainbows. And me, as an engineer, I collect that power, creating rainbow-making machines. And I give them to the astronomers, so that they can use it just like superpowers. But, just like Superman has kryptonite, well, the astronomers have Earth's atmosphere. Our atmosphere blocks some of the colors and makes it difficult to see the fainter stars. So, if the problem is our atmosphere, then we just need to bypass it. We grab this machine, we put it on a rocket and send it to space. Well, it's not that simple. These machines are very large, very heavy, completely impossible to just grab them, put it on a rocket and send it to space. Just imagine something the size of your living room. Now you grab all of that and you try to put it within a shoebox. Seems difficult, right? But that's exactly what I'm doing for my PhD, trying to understand how we can miniaturize these machines so that they can fit within the shoebox. For that, I've studied the machines that the astronomers use here on Earth, and I studied it in 3 different aspects. Spectral power, which is the capability that this instrument has to create colors that are very close to each other. For example, tomato red, cherry red, and even Ferrari red. The other is the efficiency, meaning the amount of light that comes from the stars and that it's used to create the rainbow. And finally, as you can probably tell, the dimensions of this machine. So, based on all of this, I created a new rainbow-making machine that can solve a lot of colors, is as efficient as possible, and more importantly, it can fit within the shoebox. So, there's only one thing left to do. Grab this machine, put it in a box, put it in a rocket, and send it to space, so that we can be one step closer in finding out if Earth is the only color in the rainbow of life of our universe. Thank you very much.
I feel more colorful already. So, moving on with our next candidate from KTH, Ashkan Raki, with the talk Bridging the Gap, DC Converters for Future Energy Grids. So, thank you, Ashkan.
Well, energy and electricity, they are the basis of our modern life. They shape nearly every aspect of our society, economy, and environment. You can see everywhere people have access to energy, reliable energy, clean energy. They live better and healthier. So this is the future we dream of. A grid of clean and sustainable energy. But how do we make this vision a reality? I'll tell you. Today, most of our grids rely on alternating current or AC to transmit power. But the transmission power across countries and continents will be much more efficient with high voltage direct current or HVDC. As you can see here, Europe alone plans to develop 88 DC transmission lines, and actually these lines will integrate the renewable energy into the system. And the total length, of actually this line will be will span in total length of 41,000 kilometers. That's enough to wrap around the Earth more than once. So it's a huge number. And this will actually need a huge money, around over 200 billion euro. But we cannot do this and build these lines, keep building these lines. We need some component, like DC-DC component, to interlink all these lines together to make a real grid. And this will actually make efficient the grid. So this is where my research come. Actually, I'm focused on making DC-DC converter more efficient, smaller, and cheaper by using some computational and experimental tools. Also, I optimize the topology and the structure of this converter to improve the efficiency in transmitting the power. And this makes our grid very efficient. So this helps us to create a clean, sustainable, and efficient grid, and we can have in future we will have energy that knows no border. Thank you.
Thank you very much. Our next candidate comes from, from TU Darmstadt. So Philip Schumann is looking for finding the perfect surface, right? So.
Yeah. So thank you very much. Finding the perfect surface, you might ask, why you want to do that. And this is because I want to make manufacturing processes more resource efficient by modifying their tribological properties. Why is this an important topic? Because we see a great amount of global energy loss. Currently, global primary energy demand is actually increasing by 20% until 2040, so this is big numbers. Manufacturing of all of that consumes 15% of the energy. And within that 15%, 23% are only to unnecessarily overcoming frictional resistance. So there we see a great energy saving potential, which is actually estimated up to 40%. So to use this potential, it is really important to understand friction. So what is friction? Friction, in some kind of way, is a product of our tribological system. What is the tribological system in manufacturing? It's the combination of body, our tool, counterbody, our material being processed, a lubricant in between, and our process load, usually resulting in some sliding movement. And friction is the force that counteracts this movement. So all of these components need to be understood to actually improve our system. And this can be done by modifying surfaces. Usually we want to achieve really smooth surfaces in manufacturing, but experiments could already show that sometimes, even though we have a really rough surface, these surfaces can act as a lubricant reservoir, transport our lubricant, during the transportation act as fluid dynamic cushions, apart our bodies being in contact and therefore lower friction, and in addition act as wear reservoirs. So we have wear particles that are stored in our surface roughness, our surface texture, and being moved away, and therefore elongate our surface life. So this is really desirable. This is a lot of functions you want to achieve in manufacturing, but these textures can only be artificially be designed. And this is what I want to, this is the question I'm facing in my PhD thesis. What does the perfect texture actually look like? And therefore, I'm going to investigate different process loads, different processes, do a tribological characterization, investigate different texturing parameters, do fluid dynamic simulations to come up with an optimized design, apply those textures, and in the end, hopefully see a process improvement and therefore save a great amount of energy so that also polar bears have a longer life. Thank you very much.
Thank you very much. So we are entering the final part of this session. We have our last 3 candidates coming in, and now it's the turn from our candidate from Wrocław University of Science and Technology, Radoslav Simon, with the bright future with nanowire LEDs. Thank you.
Look up. Have you ever worried about how special lighting systems illuminating our world are? Their story began in the last decade, when we say goodbye to traditional light bulbs and replace them with cheap and eco-friendly light-emitting diodes. Their heart is made of gallium nitride, the material that unfortunately is not compatible with silicon, which is everywhere, your computers, smartphones, AR hardware, and robotics. So the integration is crucial to producing less expensive, more powerful, and compatible with the modern technology hybrid system. But have you ever tried connecting Lego bricks with Duplo ones? On an atomic scale, gallium nitride and silicon is certainly such kind of bricks. Fortunately, this problem is solved by nanowires. These microscopic pillars grow together, forming a forest of billions of nanotrees, which due to their small contact area, reduce the stress between gallium nitride and silicon layers. Within my PhD, I take the next step to improve such structures even more. First, the nanowires are highly sensitive to air, which limits their performance. My solution is protective oxide shells. I showed that these shells successfully stop nanowires degradation and stabilize their luminescence over A exposure. They also increase the nanowire's brightness due to unusual quantum mechanism. And finally, they improve nanowire structure, eliminating stress and surface defects. Next, I paid my attention to the part of light which is lost, because it's emitted in the wrong downward direction. But what if we put the mirror below the nanowires to recycle this light? Indeed, I confirmed that an extra metallic layer increases reflectance, so more light goes up, increasing nanowires' efficiency. Now, my ultimate goal is to make a fully functional diode. It's challenging as it requires precise nanoscale connection. So, I will fill the space between the nanowires with an insulator, of which the nanowires stick out like candles of the cake. Then I will cover them with an electric contact, which makes them ready for the new generation of light sources. By the way, do you know that the Lego bricks and Duplo ones were actually designed to be compatible with each other? In the same way, gallium nitride and silicon were integrated thanks to nanowires. So maybe not today, maybe not tomorrow, but one day you will wake up and your room will be illuminated by billions of nanowires, revolutionizing the way we light up our world.
Okay. So the future looks bright indeed. And now we are moving to our candidate from Politecnico di Torino, Raffaele Tarantini, with the talk, Structural Health Monitoring for Seismic Vulnerability Assessment of Structures, Infrastructures, and Cultural Heritage. Thank you.
So, good morning, everyone. That's it. Good morning, everyone, again. Imagine standing in front of an old centuries cathedral, or a vital bridge, or a skyscraper. Now, these are structures that define our cities and our communities and our cultures. Now, just focus on the devastation that an earthquake can bring in just a few seconds. So, how we can deal with that? How we can provide the safe structures before, during, and after such events? And this is where the structural health monitoring comes in. SHM is just like an health, let's say, an health care of our structures. Using data sensors data analysis and artificial intelligence, we can track and we can monitor all the vital signs of our structures, just like medical staff can do in hospital. Why it is crucial? It is crucial because traditional methods rely heavily on visual inspections and theoretical models that can be time-consuming and costly. So doing the structural health monitoring in real time, we can reduce the amount of money and the amount of time. My research is focusing on developing advanced structural health monitoring strategies for structures, infrastructures, and cultural heritage, using integrating real-time monitoring with machine learning and seismic analysis. By doing so, we can track all the parameters of our structures and providing safe structures. Why is important again? Because in this way we are preserving the history, we are safeguarding communities and saving lives. As Robert Allen said one time, a generation which ignores histories has no past and no future. So we have to honor the past and we have to secure the future to the generation to come. So that's it. Thank you again.
Thank you very much. And now we have our last candidate. As you see, we made up on time. And so our next candidate is from Graz University of Technology, Rafaela Grail, with a talk, Hydrometallurgical Recycling of Lithium-ion Batteries. Thank you. Thank you. Yeah, the top arrow.
Okay. Please raise your hand if you have a lithium-ion battery in your pocket right now. I think that almost everybody has a computer, smartphone, or smartwatch in their pocket, right? All of these devices contain lithium-ion batteries. The main part of these batteries are valuable metals such as lithium and cobalt. These metals are declared as critical raw materials in the European Union. Have you ever thought what happens to these batteries at the end of their lifetime, and what happens to all of these valuable metals? Until today, the majority of batteries end up in landfills, causing a severe problem to the environment because of self-ignition, and it's a high waste of resources. A recycling concept for these valuable metals must be developed to recycle the valuable metals because of growing scarcity of finite resources and to reduce the waste of batteries. During my PhD, I'm working on such a recycling concept to recycle lithium and cobalt for new batteries. Existing recycling concepts lack of high purities which are needed for new batteries. Furthermore, there is no economic process route available because of complex recycling routes. For my recycling process, end-of-life batteries are discharged and then they are shredded to receive a black powder with which I develop a recycling process at low temperatures using different solvents. This is called hydrometallurgical process. First, lithium is dissolved by carbonated water. The selectivity, which describes how much lithium is dissolved compared to the other metals, is higher than 98%, so the purity is really high. Lithium is then precipitated as lithium carbonate and can be thus directly used for new batteries. With this process, I can recycle more than 70% of lithium. Secondly, acid leaching is done to dissolve the remaining metals, for example, cobalt. Finally, cobalt is extracted from this solution by a solvent which is called Cyanex 272. The purity of this is really high because the selectivity for the process for cobalt is quite high. Finally, cobalt is then precipitated as a hydroxide and can be directly used for new batteries because of its high purity. With this process, I can recycle more than 70% of cobalt. To design an economic process, the whole process is done in a continuously operation mode in a Taylor-Quid disconnector. You can see here in the middle of the slide an overview how the apparatus looks like. With this process, I can assure that the batteries in your pocket are recycled and you do not have to worry about the environmental impact anymore. Thank you for your attention. Thank you.
Thank you very much. So we got to the end of the contest. I would like to thank again all the PhD students for participating. I think the future looks bright ahead. We saw so many different options, things that are advancing. I feel, yeah, very, very excited and very optimistic for what is coming forward. And now, just before finishing, I would like to invite them all to stage for a quick picture. And then, so please, yeah, come up. Yes, please. No, don't put the music still. I want to say a small thing. Okay. Thank you. So we take the picture, and while we are preparing, I would just like to announce that we are now going for lunch. This will be at the rectorate, but there is student helpers at the reception that can accompany you to the rectorate, to the place where we will have lunch. So please, like, give me a small hole here. Can we fit? Yeah, we should compress. And
Maybe someone can sit.
yeah. And thank you all for being here. See you in the afternoon.